Hello, everybody. Thank you for joining us again for another session on Nanoprecise today. So condition monitoring is our topic. We've got a lot of people registered internationally and a lot of people in Canada. So thank you for joining us. Thank you for taking the time out of your busy schedules. Anyways, I'll turn it over to Ralph and we won't waste more time. We can introduce our speaker for this month.
Yes, good afternoon, everyone from Edmonton, Alberta. Thank you as well for joining in. And today we have a presentation on predictive maintenance, and you'll find it very interesting. Trusting these webinars have been useful to you. We offer them every month, and next month we will have a good webinar on torque meters, torque measuring devices. That's January 21st. So join in again at that time. There'll be time for questions afterwards. So send in your questions. Use the control bar there, and we will bring up your questions, and you can ask them of our speaker. And so we'll get on to Graham, and I'd like to introduce you to Graham. He has a Bachelor of Science in Mechanical Engineering, and he's currently Vice President of Business Development with Nanoprecise Science Corporation. He has over 15 years of experience in the areas of design, manufacturing, operations, sales, marketing, and as a business builder. He's been in oil and gas, more specifically, one of his specializations was in subsea work, and that took him around the world. He also has been involved with elevators, soil science, and reliability and maintenance. So welcome, Graham, and take it away.
Thanks, Ralph. Great to be here. I appreciate the opportunity. Andrew, I think we were going to start with a couple of polls just to kind of make sure we understand what the background of some of the attendees is. Did you want to start those polls?
Okay, here it is. You can see that on your screen. And so we'll keep that open for a little bit, maybe 30 seconds. We'll see how the votes come in. Okay, so it seems like it's slowing down a little bit. We've got a few more votes coming in. I'm going to shut this down in about 5 seconds. Okay. And here are the results. So most people, it seems like it does not apply. So maybe not in the condition monitoring realm of things. A lot of people are considering it, have not implemented yet. And only 4% have extensively used condition monitoring for rotating. So that's interesting.
Yeah. Good. Well, then that's a good opportunity to educate and show what's new and interesting in the world.
Now, I guess we also had another one. Did you want to go get a level of understanding, or did you want to do that one later?
Yeah, we can do that. Sure. Yeah.
Okay. Okay. So bear with us, everybody. We just want to, again, just to see, you know, what your level of understanding is out there in our audience.
Also gives the stragglers time to join.
Good point. Yeah, we did have a very healthy level of registrations, so hopefully people will have the time to attend. I know myself personally, I'm very guilty of registering for webinars and then not attending, but you know, priorities change all the time, so we understand. Right, very good. Quite a few people have responded already, and so we will shut this down in a couple seconds. Okay, so people like my category of enough to be dangerous.
That's me on so many subjects.
That describes a lot of us.
Yeah,
Yeah.
so many subjects.
Yeah, I would put myself in that category as well. I haven't gotten around to getting my Cat 1 yet. So, a basic understanding, but most people, 94% of people do have a level of understanding. So I think we, as you're going through your presentation, I think everybody will pretty much catch on or at least learn something. So thank you very much, everybody. We'll carry on with the presentation.
Good. So Andrew, you can confirm everybody can see that screen?
No, it's still on your webcam.
Oh. Okay.
It's blank right now. I see your cursor.
Why is it? Keeps on going back and forth. Okay.
I see your presentation screen now.
Okay, great.
The program, PowerPoint program.
I change it to slideshow.
There.
There.
You got that? Okay,
yep.
Good.
Excellent.
Technology, gotta love it. Okay, so innovations in industrial Internet of Things, that's what IIoT means. And that's a fancy way of saying typically wireless sensors that have some kind of communication and smarts in them, and applying them to predictive maintenance and specifically for rotating equipment. So I'm from Nanoprecise, but the goal of this presentation was to kind of show you what's possible nowadays rather than just pitch Nanoprecise. So hopefully we've threaded that needle, and it's not overly marketing, but obviously I'm biased. So love to hear questions or challenges at the end of this. And I guess the agenda, it's pretty clear, why is this of any interest, a little bit of background, some different technologies, what are we looking at in vibration, because this is a core piece of rotating equipment monitoring for health. The different kinds of collection methods, what's really possible these days, some examples of real world stuff that we've done, and then give you kind of an idea about, well, if I'm going to do this, how's the value created? And then if you're going to proceed after you kind of believe in the value proposition, what do you really need to be careful of if you're looking into this? And then a couple of leading things about the future that we'll just put in your brain, because that's part of my job, is to be thinking about the future all the time and seeing where things are going. So why is this topic interesting? Fundamentally, unplanned failures account for a huge amount of dollars in the maintenance world every year. Big consulting firms have estimated at over $100 billion in an opportunity globally each year. And it's not purely about just the downtime, which can be a huge part of an operation. If you have some pretty low cost piece of equipment that takes a $1 million per hour line down. Well, that's obviously a significant concern, and you want to be aware of those types of things in advance as much as possible. At the same time is, examples where if you know about something progressing to failure, then you may operate it slightly differently, to extend its life, and that can move out capital expenditure costs into far into the future, depending how you decide to operate something. And it can also allow you to avoid really expensive repairs. We have an example with one of our customers related to gearboxes, where an early stage gearbox failure might be $10,000 in repair, whereas a late stage one might be $50,000. So those are three sort of classic examples about unplanned downtime, extending equipment life, as well as reducing the cost of the actual repair or maintenance activity that all kind of come into play about if I know about what's happening, then I can look at those options and decide what I want to do. That being said, there's been a lot of people who look at process measurement to try and indicate whether or not equipment is healthy. So that's temperature, pressure, flow rate, those kinds of sensor data that you probably have in almost every process. They really are lagging indicators of anything from an equipment monitoring. They have been used in the past as sort of proxies for it, but it generally is very lagging and doesn't tell you very much about the equipment until often it's quite a bit later in the cycle of what we call a potential failure curve. So this whole topic of, hey, if I can instrument it differently and get more data about what's happening in my equipment, perhaps I can get a lot more value out of it. And save yourself a significant amounts of money from different angles that I just mentioned. So that's the why. I wanted to talk a little bit about the evolution of maintenance strategies. The history is actually pretty interesting. It started with reactive, which is you wait until something's broken and then you fix it. Pretty easy to understand. When your car starts smoking or has a squeak, then you go and you fix it, right? Same thing with machinery in any kind of industrial or commercial application. In the 1960s and 70s, NASA, aerospace, and the US military started looking at something called preventative maintenance, which is essentially on a cycle of time. You go and do certain activities to certain equipment because you feel that that's going to extend their life. Everyone's inherently familiar with this. You take your car in for an oil change every 5,000 or 8,000 kilometers, and that's what we call preventative maintenance. We do the same thing in industrial environments. The funny part about it is that aerospace and the military found that it actually increased failures in a lot of cases. And that's not every case. Obviously, that's not what happens in your car. But when you take apart equipment to like replace a bearing or something, they found that it actually increased failures because when you take something apart, you can actually introduce defects that were not there originally. So it comes back to, well, if it isn't broken, don't fix it. But how do you know if it's broken or not? So that gets into the next stage of where we're moving is more predictive and condition-based monitoring, going, hey, we want to instrument and gather information so that we don't do activities of maintenance on equipment that doesn't really need it. And then we get all those beneficial things we were talking about. And condition-based monitoring is kind of an in-between preventative and predictive, but I've lumped it all into one category here. So if somebody is sort of slicing it a little thinner, no worries, we can have that debate. The last sort of box here is prescriptive. And this is really the next gen, which is still in development in the world, where it's not even just predictive, it's now saying, hey, if you do these things, and it comes right out of a recommendation engine, where we're talking things like root cause analysis and knowing exactly which knob to turn and how far. And prescriptive is another level up even from predictive, saying, hey, you have this much life left in your equipment. Now I'm going to tell you what to do precisely in order to achieve a certain goal. And that's sort of the next evolution that is still in the works and is quite a bit more difficult than what we're doing today. So that's a little bit of a background history. And it's very much in a nutshell. So if you want to get into the specifics of that, I'm always interested to talk about the sort of overarching themes of where things have come from. So different monitoring technologies are around. So acoustics, vibration, lubricant monitoring, infrared. On the screen, you see what we call a potential failure curve, a PF curve. Some of you may be very, very familiar with this, others perhaps not. You can see that this is an image that shows, hey, failures start to begin. Oftentimes, you'll start to see that with different technologies at different points. And the point of this slide is to show that not always is one method of monitoring a piece of equipment the catch-all. So for instance, acoustics may pick up faults in mechanical components very early and show you some things, but it may not get you all the information you need compared to vibration or oil analysis or infrared. So essentially, an example of that is oil analysis may pick up water entrainment much earlier than you would see a mechanical failure with acoustics or vibration. But oil analysis is typically lagging and can't give you specificity of location. So we look at the picture and go, there's some benefits to including multiple pieces sometimes in your condition monitoring and predictive maintenance approach. And it depends a little on what piece of equipment, what application, and what you've been looking at as far as what kind of failures have you seen and how critical is this piece of machinery. You know, it's always easy to deploy lots and lots of sensors. You know, a surgical or more precise approach of, hey, how are we you know, targeting this particular piece sometimes makes more sense. Audible noise often happens much later, and then, you know, really, you know, a piece of equipment getting quite hot, you know, from mechanical failure is very much a lagging indicator. So it's just kind of an overview, and it gives you some idea about where different pieces of tech apply. This is by no means exhaustive, but these are kind of the big four from our perspective at Nanoprecise about what might apply to mechanical equipment. So vibration has been a bedrock of equipment monitoring for you know, basically 5 decades. It's been an evolving science for a long time, but it's now got lots of standards behind it. Realistically, it's foundational, and if you're not familiar with vibration analysis, essentially what we're doing is we're measuring acceleration through an accelerometer vibration sensor, where we're picking up minute changes in vibration from equipment. So think of it like this, where if you have a defect in a bearing and it goes over that spot over and over and over again. Sorry, can you guys still see my screen there, Andrew? It just switched on me.
Yeah, I can still see it. Sorry, that was a question that came in about FMEA. But we can answer that at the end.
Right. Okay. Sorry, just hang on one second, everybody. Right. Okay. So fundamentally, we're measuring it in what we call the time domain, meaning it's, you know, in time, it's measuring how much is the acceleration going up and down. And you can see a little plot there of a time domain, and it's acceleration in G's. So you see this squiggly little lines up and down, and we collect all that. And then we typically do what we call a transformation, a fast Fourier transformation, which changes that signal into what we call a frequency domain. And that's the lower image down here. And again, if you're thinking about it in terms of if that little bump in say a bearing race is in one spot and you're going over it over and over and over again, then you'll see a spike at a particular frequency on the frequency domain that will indicate you know, increased amplitude at that particular point that corresponds with that point where that, you know, a number of balls are going over it over and over and over again. And this is the bedrock of vibration analysis, where you're looking at both amplitude but also the frequency domain to go, where are we seeing spikes in the frequency domain, so that we can start to pick out, well, what is happening and what does that mean? And if you want to know more about the science of vibration analysis, there's courses Cat 1 through 4. There's a few different offerings out there that can make you a certified Category 1 through 4 analyst. We don't have time here to go through every detail on it, but this gives you the sort of basic understanding of what we're looking at. So then, how is vibration data collected? Historically, in a few different methods, proximity probes, where essentially you can see in the image there, you basically drill a probe into a housing, and it goes near you know, some kind of shaft where it will see over time you know, some movement, and it basically uses that movement between the X and the Y probe there to determine what kind of vibration you're seeing. This has been around for a long time. The progenitor of this was basically a guy named Bentley, and you may be familiar with a company called Bentley, Nevada. So he was from Nevada, and his last name was Bentley. So he invented this. It was patented in the 70s, and then, you know, at one point got bought by GE. So fairly old tech, but, you know, groundbreaking science at that point. It's evolved past that, and they still use proximity probes. They're great tech, but obviously they're intrusive. They can be very expensive, and they're not always great for a number of things like retrofits. There's also handheld probes where you can basically put them onto the outer housing of a machine and you basically collect data that way. That's what we call route-based monitoring, and it's been around a long time too. A lot of companies make probes. This is just one example here. They go from very inexpensive probes all the way to $40,000, $50,000 a piece. Then we have things like surface-mounted accelerometers that are wired. That basically you mount directly on there and they're permanently installed, and they send data back to some kind of data collection box. And then the more recent one is what we call an IIOT surface mount type device that is something Nanoprecise has in our solution. And they get mounted in a variety of ways, but magnetic base or stud mount is very common. But they have no wires, and they basically send data over Wi-Fi or cellular back to some kind of cloud platform in that manner. Some of the advantages of moving into a surface-mounted application really come back to, well, you don't have to run wires. They're quick for retrofits. If you can imagine trying to retrofit a proximity probe on an existing piece of equipment, you got to basically take apart a housing, drill it, tap it, put in these probes. It's not a very pleasant activity, quite expensive, has a lot of downtime for the process, where if you look at surface mount wireless sensors, we have literally installed 200 sensors in a day at plants, where you would get nowhere even close to that with a proximity probe. So what's possible with surface mount sensors? So this is our particular sensor. We call it the machine doctor. So very analogous to, hey, we're collecting a bunch of information and it's like going to the doctor for a checkup. And we've packaged a number of pieces of sensing tech all into one very small sensor. It's about 2 inches in diameter by about 3 inches tall. So it's pretty small. And again, it can be mounted with a magnetic base or a stud. And we're doing vibration in 3 axes. We're doing acoustic measurements, temperature for surface temperature of the equipment, and then we're also able to pick up RPM. And RPM is critical to vibration analysis because, again, if we go back to that bearing example, if you don't know what RPM you're moving at, then how do you know what frequency to look at to see if you're getting spikes from a repetitive, basically, bump on that bearing race? So variable speed machines, really, really important to have the ability to measure what RPM am I actually running at. Static machines are, where you set it at 600 RPM and it stays there forever while it's running, are slightly different, where we don't necessarily need to measure RPM, but variable speed machines are more and more common these days. We measure humidity of the internal of the sensor, and that's mostly an internal housekeeping thing, going, is the cap on correctly? And if there's humidity getting in there, then the sensor might be starting to get compromised, so we want to keep an eye on that. And then we also can measure magnetic flux, and that's mostly related to motors, where the principle is very simple, where if you have current running through wires, then you will have a magnetic field. This is how motors work as a fundamental science. So if you're starting to see changes in that magnetic flux, then it may mean that your motor has certain types of faults, meaning the current is going up and down. So we can monitor that kind of thing too. All of these sensors, there's a variety of vendors out there. We have packaged a lot of stuff all into one sensor, where there's a lot of other vendors out there that really just do vibration. And again, going back to that PF curve that we showed you a little earlier, packaging multiple pieces together allows us to do more than just look at one particular method. And that's been one of the sort of things that has taken Nanoprecise a little bit further than some of the past technology, where you just mount an acceleration probe. Now we can look at things like acceleration and acoustics and surface temperature and start to do some interesting things on the data science side to hone what kind of information and insights we gather. So the general structure of how these IoT devices get implemented is, you can see some sensors being mounted there on just a test device, little orange ones. You basically mount them, they communicate by Wi-Fi, and then they go up to the cloud, usually through a router, but we can also do a cellular version where you communicate directly to a cellular tower. That's a relatively new thing that we're just launching in the next month, but we've done the prototypes and they're working pretty well. We do all kinds of analytics in the cloud, and we'll talk a little more about that in a minute. Then we have an entire dashboard that we can show about all the different analyses that are happening. And we can also do custom outputs, and then we send alerts and alarms, email, text, or we can connect it up to CMMS maintenance platforms or other operational dashboards. That sort of data routing side is fairly straightforward these days. It does take some effort to figure out, well, exactly what are you doing and with what, but we've had lots of experience with that, and there's not very many innovative things on that side these days. So some real world examples. So this is really trying to show you that these tools and the IoT based devices can be pretty accurate. So, considering a CSI Emerson handheld probe, and they're calibrated, they've been around a long time. People trust them for route-based monitoring. They run around with them all the time in plants, and we often get asked that question: well, how does it compare to a handheld in terms of accuracy? And the simple answer is pretty darn well. You can see here in the two graphs, and we're highlighting the peak, that 10.85 from a CSI handheld. Essentially, we're identical. Within a margin of error. You're never going to have the number be exact, but this is something we did with a customer where they were basically comparing us to their existing methods, and they were pretty darn happy, going, "Wow, that's actually a little bit surprising to them that it was that good." So we were pretty happy with that, and they've decided to go pretty broad with this technology that we're offering in their plants recently. So this is just an example of how can we build trust. Well, we're happy to go toe to toe and look at how handhelds and other methods of capturing data compare. A more specific to like a fault mode. So this is a refinery pump, and again, you're seeing a couple of things. You're seeing the frequency domain over here on the left, and then an amplitude plot on the right. And you can see that there's a big spike here in the frequency domain, and this is happening at 2 times the equipment rotational speed. So it's the dominating peak is what we call it. And you can see that it's very clear, and it allows us to go, hey, this is this type of fault. And again, there's a number of things in terms of how amplitudes show up in the frequency domain that are very indicative of what type of a fault we're looking at. And a 2 times amplitude or on the frequency domain, 2 times RPM is very much a classic shaft misalignment fault mode. And on the right, you can see that the amplitude is going above what we call a fault stage 3. And those are often set by a combination of things, including international standards for what the amplitudes are for that fault 1, 2, 3, 4 levels. And then we also have some machine learning elements built into our platform that allow us to adjust some of those depending on the specific machine. So this one, we sent a notification, shaft misalignment, and this was all done in an email, and then the suggestion from our system, and this was all automated. So this is not like a human sitting in the background, reviewing all this. This is an automated system online that basically is looking at all of this data all the time, and it's sending out notifications when it sees things start to develop, and it tells you, hey, this is what we think is happening, and this is how long you have to deal with it. And we have different levels of severity going, hey, you should look at this sometime in the next little while, or no, you need to do something right now. Customer definitely verified this one in the field. So that, again, this was something where we predicted it and showed it, and then they went out and they did the inspection and they agreed. This one's a pharma, a blower gearbox combination. This is an example where it's a gearbox and it was a gear mesh fault frequency fault. So you can see in the frequency domain again there, they were seeing a real peak and a spike at that roughly 7,100 hertz. And this is where, depending on what kind of sensor you have, if you don't have enough resolution, enough high resolution frequency collection, you would miss this fault. So there are a variety of sensors out there, but if you are looking at gearboxes in particular, there can be some very specific things you need to watch out for. And one of those is if you can only collect data up to 2,000 hertz, then you're going to miss spikes like this in the 7,000 range where you just won't see it. And that's just sort of math. It's not an opinion. And again, we told the customer in advance, and they basically went, great. They went and looked at it, and they verified this. And this particular blower gearbox combination, if it goes down unexpectedly, it costs them about $100,000 an hour for that process when it's down. This is another example where we're looking at bearings specifically, and this is that example we're talking about, an outer race failure, where you can see different spikes on the frequency domain in red there, where it's showing multiples, and that's a classic one where we're seeing harmonics in the frequency domain. And this is where, again, going back to the science of vibration analysis, and this particular pump, again, would have been about 200 grand an hour for downtime, which is, again, why they really wanted to monitor it. And we didn't give them as much notice as we would typically like, but in this case, they at least had 24 hours. And it doesn't necessarily mean that it's going to explode, but they're moving towards a pretty severe catastrophic failure, where you're going to encounter either big costs or it could actually fault and be shutting down. This is a recip compressor. So this one's a misalignment. You can see the sensor there on the top. Compressors are, depending on the compressor, a little more challenging in some cases for some of these surface mount sensors, because they have what we call a journal bearing or fluid film. And we've been able to show that we're able to monitor those types of applications, but it is a little more challenging, and you need some software to pick out faults. Looking at just pure vibration data and not looking at it in certain ways makes it a little harder to pick out on journal bearings, but we've got a system that basically is able to do that. So some of those are even possible, where you may encounter some people who say you can't do fluid film bearings or journal bearings with surface mount accelerometer type systems, and we would disagree. So how are we creating value and return on investment with these types of systems? So this is an example. Your particular plant or equipment set may vary. In this example, it's okay. Well, I have 429 semi-critical machines in my plant, and semi-critical is a definition only you can really decide upon. And semi-critical in our world is often, well, if it goes down, then I care quite a bit, and I can't stock every part for every machine in my facility. And the average 2 to 10 hours of downtime, and the cost of downtime, even modestly at $1,200 to $12,000 per hour. There are some applications that's way higher. So that can make a pretty big range of between $1 and $50 million for a plant of total cost of downtime. So, and if you can apply predictive maintenance to reduce that even modestly, then it's pretty easy to do the math going, hey, if you applied essentially 4 sensors on each set of machinery, so 1,200 sensors, it's about 300 grand a year for our services. Even if you're only losing $1 million an hour a year in downtime costs, then that's still a 3 ROI immediately. And if you're anything higher than that, then it just goes way up from there. Predictive maintenance costs, they've been studies by a variety of different organizations, from Chevron to the military to a variety of others, where it's really, they've come to a number of about between 25 and 40% more effective and less costly than preventative maintenance, where you're routinely going out and just doing operations whether it needs it or not. So essentially the mantra is, again, if it isn't broken, don't fix it, but make sure you monitor it. So this is where we talk about the value of automation. So we say, okay, well, you're going to put a whole bunch of sensors on machinery. Okay, great. We're going to collect a lot of data. Then what do you do with it all? Historically, if you were doing route-based monitoring, you might go to a machine once a quarter, maybe once a month, and collect, a pretty small amount of data for a couple of minutes. That's pretty easy for somebody to, wrap their hands around if you're an analyst. But now, say we're collecting data multiple times a day on hundreds or thousands of sensors. So this is a pretty low end, a low number. So 100 machines, permanently installed sensors. If you're collecting even twice a day, that's 73,000 data sets to review. Even if an analyst only spent 5 minutes, that's 6,000 hours. So it really comes back to the only way to really get to full value on these kinds of installations is to automate the review in some way. And that is now possible. Nanoprecise is one of the sort of front runners of doing that. We have some competitors where they're basically stacking loads of people in a room and looking at all the data. We've taken the approach of let's automate this as much as possible to make it as cost effective as possible. So the different levels of automation can go from, well, you just grab the data and you look at it as and when you get time. We feel that you're going to end up with a probability of catching all the faults being pretty low. So, that kind of approach, yeah, okay, you have sensors and you have data, but who's looking at it all the time? The other approach is just looking for anomalies based off what we call overall vibration energy, meaning is it going high or low? And that's quite common, but it really leaves you almost, I would call it with one eye, instead of two. And you're going to miss all kinds of things and also have a lot of false positives. So it's one of these things where if you've ever been in operations, if you get a whole bunch of notices from a system that says that there's a problem, and then you find out that a whole bunch of the time it's not true, how much trust do you have in that system when it sends you the alert the next time? So I call it the cry wolf effect. And this is what we're always trying to find the balance of. We don't want to miss things, but we don't want to send a whole bunch of alerts that are not real, because false positives also sap confidence in the system. So just doing auto anomaly detection, we feel drives the behavior of they're not going to end up paying attention to the faults that really matter at a timely manner, because they're going to end up with a lot of false positives on a pretty regular basis. And that's not an opinion. That has been true historically, and we talked to a lot of customers where this is one of the reasons they've been disillusioned with this type of stuff in the past. So then you move into things like auto fault characterization, where you're actually picking out faults with the kind of analysis where a person would do it, but again, Nanoprecise has basically put that in a box and been able to put it into an automated software. And then the last sort of piece is, okay, well, you've got the fault mode, fine. Now, is it severe enough that I need to do something right now, or can I wait? And that's that last little bit of how are we deriving the maximum value out of this. And you're never going to get to 100% certainty, because that's just sort of something that isn't available in the world. But you can get a lot more certainty by being able to pick out a particular fault mode and then understanding how is that fault mode progressing, and is it moving fast or slow? So building all of these things into your automation of review of this data is really the game changer, I think, in what is now possible. Putting a sensor together, it's been possible for a lot of years. But how do you deal with all that data and deliver insights that are actually valid and don't have a lot of false positives? That's been challenging for a lot of people for a long time. So say you're going to get into this. What do you need to consider carefully? A sensor really does not equal a solution. So again, how you're handling all this data analysis. Wireless networks, they're really important to getting this stuff to work properly. So putting sensors on and using IoT sounds great, okay, but what's the underlying need in order to make it work really well? And wireless networks really critical to make sure that you get what you're looking for. False positives drive a lot of sort of poor behavior in operational teams, so try to minimize those as much as you can. And then how do you turn information into action? So insights are great. So we deliver all this information to you, or send alerts. What happens to it? Does it go into someone's inbox and they happen to be on vacation? How do you operationalize it? And there's a number of things you can do to integrate it with operations, and one of those is connected up to a CMMS system. There's lots of vendors out there. We have a partnership with a couple of them that we think are quite good. You may know one of them that just got acquired by Fix. They're a Canadian company, FIIX. They got bought by Rockwell Automation. But we've worked with others, the IBM system and a few others. So depending on what you're using, piping alerts and information into that so that you can actually have work orders generated and track all the information is something we can do these days as well. So what's next? What's the future looking like? Battery life on sensors, especially for wireless ones, is often a concern that comes up. We're innovating in that space, and lots of other people are too, to get as much battery life as you can out of these sensors. Right now, we're in the kind of 1 to 6 years, depending on the application and what we're doing. We have a few things coming out in the new year that will take that probably more up to between 3 and 12. And we think that that's going to be a bit of a game changer as well. Cellular communication. So we talked about Wi-Fi networks, and what you have to do to make these things work well. We have a number of people who've been asking us about a cellular version of sensors, so that especially for like mobile applications, so yellow iron or lift trucks or other things that are moving around, and Wi-Fi is not a great solution for that. So there's a number of cellular IoT solutions that are going to be coming out in the near future from us and from others. We think that's going to be quite interesting too. Integrations with systems, processes, and workflows. So, taking these insights and pairing them up with process data to look at process optimization, I think will be an interesting area in the future. Again, those workflows from CMMS and other things related to operations, I think is going to be a lot more interesting. And one that I'm really watching closely is something, remote inspection. I don't know if anyone on the call or the webinar has been watching some of the Boston Dynamics robotics coming out, but it's quite interesting. They have this little robot dog called Spot. And I'm looking at that going, at what point do drones or robots like that get notified immediately as part of that workflow integration where, an operator person doesn't even go out to inspect initially? It just gets a notification, and then the little dog trots off and goes off and takes some pictures and video, and brings all that back and pumps it into the system, and then somebody can look at it at a later date or a later time. And I see that as being quite an interesting application of robotics in the near future. And you basically avoid health and safety concerns, and you get immediate action, and you don't have to wait for somebody to go out there. So I see all those as interesting, and I'm sure there's much more, and love to hear feedback about where people see maintenance and predictive maintenance going in the future. But these are certainly a few things that we're watching that I think are quite practical. So with that, I think I'm pretty bang on time there, huh, Ralph? You're supposed to be the timekeeper, but I think I'm doing pretty well.
Yes, you're doing very well. I got 43 minutes in, so we have time for questions.
And we do have some questions, actually. So I apologize, Graham, when I interrupted your presentation. I assigned a question to you, and I didn't realize it pops up a window. But that first question from Steve Rashford was FMEA. It says, will be the best approach on which technology to deploy? And that, I think, was when you had the PF curve up, when that question came in.
Right. Sorry, could you rephrase the question? It's, maybe I didn't understand it.
So he was just talking about FMEA, and so he's saying, he's asking, when will it be the best approach, or will be the best approach on which technology? I guess maybe, what?
Yeah, so I'm not sure that's a question or a statement, but I would agree. I mean, if you're, FMEA, or if historically that you've had certain types of problems with certain types of equipment, then yes, absolutely. Yeah,
Steve, I unmuted you, so if you wanted to elaborate, you feel free to.
Yeah, and that's all I was alluding to, is just that, yeah, when you're looking at equipment and you're wondering which technology to deploy, rather than just, finger pointing at one particular thing or applying them all, that usually if you go through an in-depth RCM analysis or FMEA, it will usually lead you down the path to selecting the right technology on what to deploy, and then obviously you will learn over time and adjust the frequencies accordingly. That's essentially all I was getting to with that point.
Yeah, makes sense. I mean, knowing the equipment and understanding the application is fundamental to knowing what you should be trying to deploy or not.
And just one other question while I am unmuted. In regards to the sensors, you said that the sensors and included with the analysis. So is the intent behind your platform to purchase or contractually obtain the sensors and Nanoprecise essentially does the analysis and just will come back to the end user and say, hey, this is what we're seeing. So you guys do it's basically an all-inclusive approach?
Yeah, that's correct. So it's not to eliminate an analyst, but it's to basically do the grunt work. That is, you really just don't have enough time for your analyst, and so they can go in and look at all the nitty-gritty details. We're not a closed black box. We want to show them the reasoning, because inherently humans, we still feel, are an important part of decision making in any of these things. Only they can really decide what they want to do with the process, and if they feel they don't understand where the data is coming from or the advice, then they generally have a hard time trusting it.
Absolutely. Okay, perfect. Thank you.
So I don't know if you can see, Graham, the other questions that were sent to you.
Yeah, so RPM, specifically, we have a magnetometer, so it's based on a Hall effect. So you basically place a small neodymium magnet that doesn't cause any imbalance on an exposed shaft, and as long as the sensor is within 4 inches of that magnet, then it will basically pick up that rise and fall in a magnetic field, and it can basically get 99% plus accuracy on RPM. I think the next one, can we hardwire the router to the DCS? Not typically. It depends a little. There are IoT platforms that we've worked with where we basically send the data directly to those, and then they do the amalgamation with any kind of DCS data. There's a whole bunch of companies out there that do that. So we are not an IoT platform company, but we're happy to work with those kinds of firms. There's Relayer, Litmus, ThingWorks. I could list off a dozen. That would basically be able to pair up that kind of stuff, and combine different data. Our focus is rotating equipment and analysis of that data, and then we pair it up with other people's information and operational aspects to try and derive whatever a customer might be looking to achieve. But fundamentally, we're highly focused on predictive maintenance. How are we able to accurately predict remaining useful life? Great question. So a lot of that comes back to the trending, going, hey, what are we seeing over time? And this is where permanently installed and collecting data over time so you can see how something is progressing is crucial in order to being able to do that. And remaining useful life is different than remaining time to failure. Slightly different terminology, and they get confused a lot of the time. So failure also has an interesting sort of definition and question, going, well, what's a failure? Is a failure explosion, or is failure getting to the point where it's going to cost me a lot more to repair it or not? So remaining useful life is basically going, hey, you're getting to a point where this equipment is no longer in good shape, and it's definitely worth thinking about whether I want to run it to failure or if I want to do basically maintenance now. And running to failure is a totally valid operational strategy, as long as you understand that when it goes to failure, it could be quite abrupt. And those are always calculations that go, well, is it a $1,000 pump or a $50 million gas turbine? Running a gas turbine that's $50 million to failure is not a very good decision. Running a $1,000 pump to failure, probably okay. So it sometimes depends, but the accuracy comes from that trending and then looking at all these staged faults and then knowing exactly what fault mode we're looking at, because different fault modes will progress at different rates a lot of the time. So not knowing the fault mode definitely makes it less accurate. So are we 100% accurate? No, but are we a lot more accurate because we know the fault mode? Yes, we are. Next question, are the algorithms limited to supervised learning or linear regression? Okay, so this is getting into a little bit of depth on, and we use a variety of algorithms. So I think I'm gonna have to demur on that question and go, Hector, if you wanna go through more depth about supervised learning versus regression versus other things, I think we might need to book a meeting offline because that's a whole nother topic. And then I think he had a follow-on question there. Are you capable to predict multiple compressor train with neural network? I'm not sure I understand the question, Hector. We might want to, I don't know, can we unmute Hector and just ask him to maybe elaborate where he's coming from?
Sure, let me just do that here. Go ahead, Hector.
Hello everyone. It's been a while since I've been talking to you guys, so glad to see
Yeah, nice
everybody.
to see you again.
We actually has been working a lot with supervised learning and in terms of linear regression and multivariable regression on algorithms, and and that's actually pretty good when it comes to individual equipment. But what we essentially realize is when it comes to compressor training, that doesn't fit the purpose. So in most cases we gotta essentially go to what we call neural network. But when you start counting the true positive and the true negative, and the false positive and false negative, it's just like it doesn't it is pretty close, but it doesn't fit entirely the purpose of predicting the failure correctly. So I just wonder if you guys have some experience in that area and how you guys has been able to explore that.
Yeah, I mean, we go at it from a component perspective, looking at each individual component to go, where is it at? If you're looking at more of like an overall process optimization or overall process perspective, that is more complicated. And so we've gone from the approach of component by component, looking at each individual item. And that we found is better than a statistical model where, neural networks are great, but as you're probably aware, Hector, they require a lot of data input. And it's, a lot of data has quality control issues in terms of where is it coming from, how good is it, is the time stamping even correct? A lot of this stuff comes from like SCADA and DCS, and
that's exactly right.
Time stamping is wrong.
Yeah, I think what we figure is just the scale. When you start looking at different pattern of potential failures on different systems, especially on auxiliary systems for machines, you essentially start to come across that, for instance, you're gonna have temperature or pressure that's gonna be in one scale, and then when you try to put flow in there, it's gonna be a different scale. That's gonna mess the complete neural network. So it's pretty tricky to essentially correlate those numbers, but so that's essentially what's my question.
Yeah, and it is super tricky. And I know of people that claim that they can do it, and I'm still a little dubious. So we've come from the other side.
I was hoping for you to say, yeah, I can do it. So I was like, okay, we're done here.
I wish, but that's the funny thing about data science and a lot of these tools is people think they're a magic wand and they're really not.
It's not. Yeah, you're right. All right. Well, thanks for your answer. Appreciate that.
We'll maybe get there in a year or two, I suppose.
Yeah, maybe. Yeah.
There's one more question that came in through the private chat. So, how do you minimize the false positive alerts? As the question.
Right. So that comes back to, again, going from what we call an overall vibrational energy monitoring, which a lot of people do. So they call that RMS. So they basically go, okay, well, we're going to take that acceleration and we're going to basically normalize it by doing, what we call a root mean squared math conversion, which is very simple. And they basically go, well, if that's low, then it's fine. And if it's high, then I want to send out an alert. But just monitoring RMS does not necessarily mean there's a fault. And the simple example there is, well, if you change the process conditions, perhaps the overall vibrational energy goes up. But that doesn't necessarily mean the equipment is failing. It just means the process changed. So how do you tell the difference? And the simple answer is you have to look at multiple different sensing elements. And that's why we use acoustics, vibration, and temperature, as well as RPM and variable speed machines to look at, well, what is actually happening with this machine, as opposed to just looking at vibration alone. So that helps a lot to start with. Then the second part is when you're looking at the analysis itself, if you're going into a specific fault mode characterization, because you have all of that rich data and you're combining it together, you can pick out fault modes specifically. Then you can compare that to fault mode specific thresholds and monitor each one individually. And that again gets you another level of certainty. So we're looking at multiple levels of data coming in and then looking at very specific analyses to go, hey, what are we really seeing here? And then we can compare an actual fault mode against characterized threshold levels And that again is another level of refinement. So it's sort of a stepwise approach of, let's make sure there is a real fault. Then let's make sure we understand what that fault is. And then we compare that fault to very specific thresholds, and it gets you that more certainty. So is it 100% accurate? We can never make that guarantee, but we're a lot more accurate than just overall looking at RMS.
There was an earlier question from Mohammed, and he's asking what is the wireless range and the installation requirements for the sensor?
Right. So sorry, go ahead, Ralph.
Perhaps for the sensor plus whatever the next step is.
Right. So the wireless range depends a little on the router itself and then what's in the way. So if you have line of sight, that's one thing. If you have a steel wall in between, that's another. But typically 30 to 50 meters away from a router is pretty good. And, we can install routers in various locations and repeaters to get around different locational challenges. The wireless hardware is not typically the biggest expense long-term. It does have a cost, but it's typically not the biggest issue from a cost point of view. It's just, you got to do it. And then you have to have reliable routers that I hate to say it, but we've had people even, just kick power out from the router. And then they ask, why does, 20 sensors down? And we're like, well, I can't keep you from kicking the power out of the router.
Yeah.
So there's a few challenges there, but does that answer the question, do you think, Ralph?
I think it does. Well, and I guess I also want to add too that, when you're first, looking at deploying sensors in a plant, let's say, and you have existing wireless infrastructure, there's apps where you can go around and just check the signal strength, make sure that it's adequate. And of course, adding access points is relatively cheap, and it's worth the investment so that you can get the transmission rates up high, because that's going to affect your battery life significantly, right? So, the faster you can send data, the less time it has to stay online, and therefore your battery lasts a lot longer. Anything else to add to that?
No, that's exactly right. I think, Steve, is there any appetite for process data collection plants? Possibly. I think we probably mesh with a lot of things that are already in existence, but you never know. There's a lot of plants out there with already instrumented processes. And again, there's IoT platform companies where they basically amalgamate all this data together. I think we would probably look at that approach rather than, becoming a pressure temperature sensor company. Like there's a lot of commodity pressure temperature sensors out there. I don't think we're going to be looking to make one of our own, but including that data in some way to, optimize a process. Yeah, sure. Let's look at it. There's a question about a little more information on sensor mounting methods. Really simple is we can do epoxy to glue it to something essentially, or adhesive. Glue is a really bad engineering word, sorry. We can also do what we call a magnetic base, which basically, sticks onto ferromagnetic materials. That's the most common. And then a stud mount, meaning it's got a little threaded stud, basically a 1/4 inch 28 thread per inch stud, really common. So those are the three most common methods. And I would say the most common is out of those three is still a magnetic base because it's super easy to do.
Well, I guess I should have mentioned that Spin Doctors is a distributor of Nanoprecise technology, but I didn't want to take too much from that. But basically, yeah, you've got the magnet that threads on, but better yet, you want to be able to thread that directly to it, and then add the epoxy as epoxy and threaded, and it really shouldn't go anywhere. But you definitely want to have a strong, proper solid installation. If you're putting on a rough casting and it's rocking around, well, that noise is going to reduce your accuracy of what you're seeing.
Yeah, and that's where sometimes we do a combination even of magnetic base and epoxy to accommodate those kinds of things too.
That's right. And then, well, Matthew was asking about, the extreme temperatures and whatnot. And of course, yes, it does affect the sensor and the battery. There are physical limitations. We have technical specs that I can send you, Matthew, as well.
Yeah, exactly. So, I mean, if you're going to have the sensor operating in -40 all the time, then obviously that's a slightly different animal. And we can look at some of those things. You know, we have a couple of things coming out in the new year that are, I think, quite interesting that might kind of deal with that concern entirely. And that cold temperature on batteries is the major concern. Essentially, we're good up to about 120 C. So that's typically not the, you know, anything that's over 120 C environmental is pretty severe.
There's a brochure attached. You can find it on your control panel, and it's about 6 pages long. It gives quite a bit more information on the technology and on this product.
So we are at the end of our time slot, but if you do have any more questions, if you wanted more information about the technology, there's a survey. You can let us know if you want to be contacted. We can do that and provide any more information. So I'll let you guys have your closing words, and we'll see you back in January.
Great. Well, thanks for the opportunity. Good to be part of the webinar, and thanks to Ralph and Andrew for inviting us.
Yeah, thank you for coming.